Good morning, everybody. Hopefully, everybody's able to find their access to today's program. Today, we are sponsored by Biochem Animal Nutrition and Health. And the focus of today's session will be on the footprint of animal agriculture and how to mitigate the impact to achieve a carbon neutral production system. My name is José Santos. I'm a professor in the Department of Animal Sciences. And throughout the day, you'll have a chance to send us questions that will be addressed by the roundtable members in the second part of today's program. So on the bottom of your Zoom platform, you have a window that says Q&A. Just click on that and send us questions that we'll hope to be able to address. If not today, we'll address at a later time and send to you. You will notice that many people already sent questions after they listened to the pre-recorded presentations, and we already populated them. So we'll have 4 presentations this morning, 3 of which you have already had the opportunity to review in the pre-recorded sessions that were sent to you. We'll start the day with Dr. Frank Mitloehner from University of California, Davis, followed by 3 short presentations that are summaries of what Dr. Juan Tricarico, Jim Wallace, and Caleb Harper presented in their pre-recorded presentations. We'll have a 10-minute break, and then we'll resume with a roundtable discussion until 2 p.m. Eastern Daylight Time. So with that, I'll turn the microphone to Scott Sorrell from Biochem, who will introduce our first speaker.
Yeah, thank you, Jose, and thank you everyone for joining us today. My name is Scott Sorrell, and I'm the Director of Global Marketing for Biochem Animal Nutrition and Health. At Biochem, sustainability is at the heart of our corporate vision to make the world a healthier place. Throughout our history, Biochem has been focused on environmental stewardship and sustainability. In 2020, we joined the United Nations Global Compact to take that to the next level. Today's presentation will move the vision forward for the entire ag community, and will bring some practical and executable ideas to the forefront. To get us started, I'd like to introduce our first speaker, Dr. Frank Mitloehner from the University of California, Davis. Dr. Mitloehner is a professor and air quality specialist in cooperative extension in the Department of Animal Science at UC Davis. Frank is also director of the CLEAR Center, which leverages 2 core principles of research and communications to help animal agriculture operate more efficiently to meet the demands of growing population and lessen its impact on the environment and the climate. Research topics include quantifying and mitigating greenhouse gas emissions for livestock. Frank has served as chairman of a global United Nations Food and Agriculture Organization hosted partnership project to benchmark the environmental footprint of livestock production. Dr. Mitloehner received his master's degree in animal science and agriculture engineering from the University of Leipzig, Germany, and his PhD in animal science from Texas Technical University. Frank was recruited to UC Davis in 2002 to fill the first ever position focusing on the relationship between livestock and air quality. Dr. Mitloehner, please take it away.
Thank you very much for the introduction. So it's a real pleasure talking to you today about a topic that's near and dear to my heart. It is the impact of livestock on climate, and here in particular, the impact of methane on climate. I think that there are important changes in and around our understanding of what biogenic methane does to our climate. And because methane is the Achilles heel of animal agriculture's environmental footprint, I want to spend some time on that today. I titled my talk Rethinking Methane, the Path to Climate Neutrality, and a peer-reviewed paper of the same title will be in the peer-reviewed literature in the next 2 weeks. Before I get started, just some background and some other info. I'm on Twitter, GHG Guru is my handle. My center, the CLEAR Center, is also on Twitter, UC Davis CLEAR. I want to let you know that what I'm about to present has also made its way onto YouTube. We produced a video, a 5-minute video called Rethinking Methane, and I encourage you to watch that and share it. Just last week, I was interviewed by a YouTuber, and that was quite an experience. And this YouTuber put out a video called Eating Less Meat Won't Save the Planet, and here's why. I could not believe my eyes. Within a week, this YouTube video was watched 1 million times. 1 million times. So I encourage you to please watch that and increase those numbers further, because it's important that we get the news out as to what the impact of livestock is on our environment. Our consumers oftentimes see data depicted, such as those here in the world in data, comparing various food items, such as beef on top, and then lamb and other food items. And if you go down the list, you see tomatoes and bananas and everything, compared to one another. If you look at the bottom there, it says greenhouse gas emissions per kilogram of food product. Now let that sink in for a second. Greenhouse gas emissions per kilogram of food product. There are people comparing a kilogram of beef to a kilogram of tomatoes or bananas and the related greenhouse gases across those different food items. It should be clear to everybody, that this is not a fair comparison, not even an apples to oranges comparison, but an absurd comparison of a very nutrient-rich food item to others that are pretty much largely water. But that's not it. That's not the only criticism I have on a slide like this. And this has made it all throughout the world media. It's also depicting a global average of these different food items. So this is not US beef or so, this is global beef. So why is that a problem? Well, let me ask you this. If I were to ask you, what are the emissions of a car? And I just leave it with that. What are the emissions of a car? What would you say? You would probably say, well, a car driven where? In California, in Ethiopia, in China? A car driven by whom? An 18-year-old or an 80-year-old? What make and model? How old? Combustion engine, electric? And so on and so on. Many, many questions need to be answered before you can come up with an answer to what are the emissions of a car. Why would that be different when it comes to beef? How can you just put out emissions of beef globally and claim that that has any relevance to any place in the world? It doesn't. Even more important than those two criticisms is, if you look at beef here, that there's a large area depicted in brown. And that large area is methane. And methane is what I'm about to talk about. The United States is a significant contributor of greenhouse gases worldwide. Worldwide, all human activity amounts to 49 gigatons of greenhouse gases. 49, almost 50 gigatons. That's a large number. The United States is responsible for 12 of these 49 gigatons. So 12%. And of the 12%, you see the 11 of the 12 is fossil fuel use. That's oil, that's cars, trucks, trains, planes, ships, power plants, cement industry, and so on. That makes up 11% of global greenhouse gas emissions. And then a little bit over 1% of global greenhouse gases are caused by the US food production and consumption sector. Okay, so a little bit over 1%. The reason why I put this up is because oftentimes I read in the media the notion that what we eat, what we produce, and what we eat in this country, food-wise, is a huge determining factor of the world's climate. Animal agriculture, as you can see in pink there, makes up 0.5% of global greenhouse gas emissions. If you want a percentage of animal source foods to US greenhouse gas emissions, then we need to look at this slide here. This is from the EPA, and it shows data from 1990 to pretty much recent. And what you see there at the bottom, in orange, that's the contribution of our beef supply chain to total greenhouse gas emissions. It's certainly not nothing, it's something, but definitely not a contributor that determines the climatic impacts of our society. Okay, we do have a contribution of beef, and that's in orange, or light blue, that's the rest of animal agriculture. But what we read day in, day out is a total exaggeration as to what the impact of what we eat is on our climate. What you see here in this reddish color, orange or reddish color, are other sources, and that's largely the use of fossil fuels, oil, coal, gas, and everything that uses oil, coal, gas, such as gas trucks, trains, planes, ships, power plants, and so on. So it's pretty clear as to who the 800-pound gorilla is. At least it's pretty clear to me. And but that's not to say we should not take care of greenhouse gases from animal agriculture. We should, and we need to take care of our house as well. But let's take a look at what the majority of that orange color here is made up of, and that's methane. Greenhouse gases such as CO2, methane, and nitrous oxide are generally compared to one another using a unit called GWP 100. GWP 100 is a unit that was invented back in 1990. It converts methane and nitrous oxide by using these factors here into CO2 equivalent emissions. So let's say if a farm were to produce, let's say 10 tons of methane, then all you need to do using this unit is multiplying the 10 tons that farm produces times 28, and you achieve, or you arrive at the so-called CO2e, CO2 equivalent amount of that 10 tons of methane, which is 280 CO2e units, okay? So this unit, GWP 100, has received a lot of criticism, particularly recently. And the reason for this is that in addition to being a potent greenhouse gas, as you see here, depicted by this 28 number, methane is also quite different with respect to how it warms the planet, how it does that, its behavior in the atmosphere, and the impact it has on warming. And I will explain in just a minute. So you can see here, nitrous oxide is even more potent than methane, considerably more potent, but that's not something people want to talk about as much. So how is methane different from other greenhouse gases? Well, this here shows the global methane budget. On the left side, you see various sources of methane, such as fossil fuel production and use, agricultural waste, biomass burning, and so on. They amount to a total of 560 teragrams globally. And this is where much of the reporting in the media stops, ends, when indeed methane is not just produced by these emission sources, but on the right side you see there is a significant atmospheric removal. That's what it's called, atmospheric removal of methane. And that's facilitated by various sinks. And you see those sinks amount to 550 teragrams. So 560 are produced, 550 are destroyed. That means you have to subtract the one from the other, and then you arrive here in red at the total net methane in the air. And that's 10 teragrams. Still a number that's too high that we seek to reduce, but obviously a totally different narrative when you actually look into atmospheric removals. And I will explain that in more detail in just a minute. But remember, methane has atmospheric removals associated with it. The other greenhouse gases, CO2, nitrous oxide, do not. And that's what makes methane very different with respect to how it impacts our climate. When you look at the sinks here, you see a large arrow pointing downward. And underneath it says sink from chemical reactions in the atmosphere. That's that atmospheric removal I talked about. And it's called oxidation. To be precise, it's called hydroxyl oxidation. And that's the process by which a methane molecule in the atmosphere meets a so-called hydroxyl radical. A radical that steals the hydrogen away from the methane, CH4, and destroys methane. Okay, and that generally happens in and around a decade. Okay, and that leads to a situation where methane has a different lifespan compared to those long-lived climate pollutants CO2 and nitrous oxide, which live 100 or 1,000 years, respectively. Methane, approximately a decade. Okay, why is that different? And how is that different? And why does that matter? The answer comes soon. But before I go there, I want to explain to you where the carbon that goes into methane, CH4, where that carbon comes from and where that carbon is going. And I display here the so-called biogenic carbon cycle. Some people call it the biological carbon cycle. It starts with plants and what plants need to grow. They need sunlight, they need water, and they need a source of carbon. That carbon they receive, those plants need, comes from the atmosphere in the form of atmospheric carbon dioxide, CO2. That carbon makes it into plants, and there it's converted into carbohydrates, such as cellulose, the world's most abundant biomass. or into starch. The only animals that can make use of cellulose, by the way, are ruminants. And so these plants convert the carbon into cellulose or starch, and then a bovine comes along, eats that plant material. And it doesn't really matter whether that's this grass here or whether it's corn or soy or something. These are all plants that, while they were alive, assimilated carbon. So this animal, this bovine, now eats that plant material, the above ground material, and some of that carbon contained in that plant material is then converted into methane, CH4. So the question now is this C in the CH4, in the methane, that carbon, is that carbon new and additional to our atmosphere? And the answer is no, it's not. Because this carbon here, this carbon molecule is identical to what it was before when it was in the atmosphere. A constant herd of livestock, listen to my words carefully, a constant herd of livestock does not add new additional carbon to the atmosphere. What it does is it recycles existing carbon around and around and around. That is a constant livestock herd. If we were to increase the number of livestock, then we would add new additional methane and hence new additional warming. But a constant livestock herd, let's say constant beef or dairy herd, will not add additional methane emissions. And that means no additional methane concentrations. And that means no additional warming. Constant herds do not cause additional warming. What happens to that methane? After about 10, 12 years, that methane is then converted via hydroxyl oxidation by these radicals I talked about into CO2 and water. So now you will say, well, how is that a good thing? You just told us methane has a lifespan of a decade. CO2 has a lifespan of 1,000 years. It's not about a good or bad thing. The question here really is the carbon that's generated by cattle when they produce methane, is that new additional carbon added to the atmosphere, or is it not? And the answer is it's not. It's recycled atmospheric carbon, making it through plants, then into animals, they produce methane, and then it goes back to CO2. And then goes into the CO2 pool in the atmosphere from which plants draw CO2 during photosynthesis again. So this is the biogenic carbon cycle, a cycle that's very, very different from the culprit, the main culprit of a changing climate, which is the use of fossil fuels, oil, coal, and gas. And how does this one here differ from that fossil fuel situation? It differs very significantly because fossil fuels are ancient forests and animals such as dinosaurs that died, decayed, and fossilized and accumulated in the ground for a long time. Over the last 70 years, 70, we have taken about half of all that carbon in these fossil fuels out of the ground. We extracted it, we brought it up, and we burned it with cars, trucks, trains, planes, ships, power plants, cement industry, and so on. That is a one-way street, adding new additional carbon to the atmosphere. On the livestock side, we are recycling an existing carbon round and around and around, at least as long as we have constant herds. But every time we burn fossil fuel, we add new additional carbon to the atmosphere. This is why you should never compare a cow to a car. Totally different, completely different scenario, okay? So now colleagues from Oxford University said, first of all, they acknowledged that methane, particularly biogenic methane, is very different from other greenhouse gases such as CO2 and nitrous oxide, and they started a discussion why GWP 100 is not appropriate to be used to characterize the impact of methane on climate. They started a new unit called GWP Star. And this new unit, GWP Star, actually looks at the impact of methane on warming. And remember, warming is what it's all about. It's not really about carbon footprint. It's about the warming footprint of a sector, because the Paris Climate Accord and others are not trying to limit nations on carbon, saying you have to emit so and so much carbon, but what it's all about is to limit our warming as human community below 2 degrees centigrade. That is what the Paris Climate Accord is about. And that's what our sector should thrive for, to reduce our warming footprint. Bill Clinton once said it, and I think he said it pretty well. It's the warming, stupid, he said. It's the warming, stupid. Because people kept talking about the carbon, and he said, it's not about that. It's about the warming impact of a sector. And I agree with that. So this unit, this Oxford group around Miles Allen, Professor Miles Allen, who is also IPCC senior author, said GWP 100 is not fit for purpose to predict the impacts of methane on climate. So they produced a new unit, as I said, GWP Star. And they said that GWP 100, the unit that's currently used, overestimates methane's warming impact by a factor of 4. By a factor of 4. And I agree with that. And GWP 100 does not allow you to depict the impact of methane when you decrease methane at all. And you will see that in a minute. And last not least, GWP Star does take into consideration the atmospheric removal of methane. Okay, GWP 100 does not. GWP 100 acts as if methane were only produced but not destroyed. It leaves that important part of the narrative out. And that is why GWP 100 is not fit for purpose. You have to account for the atmospheric removal, and I will give you an analogy in just a second. I want to contrast here two gases, CO2 versus methane. Imagine you were to drive to work from home. On Monday, day one, you drive, you burn gas, you put CO2 into the atmosphere. On Tuesday, you do the same thing again, and you add new additional CO2 to what you put out on Monday. So this is the same on Wednesday. You drive again, you produce more CO2, and that's added to the existing stock you put out on Monday and Tuesday. Hence, CO2 is called a stock gas because it accumulates in the atmosphere. You see, this is like a pyramid. Every time that you burn fossil fuel, you add new additional CO2 to the atmosphere, and that causes new additional warming. Now, this GWP 100 that I talked about at length already is treating methane as if methane were to do the same thing, accumulate in the atmosphere. And the reason why it treats it that way is because GWP 100 does not take care of atmospheric removal. But is methane the same as CO2? Does it accumulate? The answer is no. Methane is produced and it's destroyed almost at equal rates. A constant emission source of methane leads to constant concentration, and that leads to constant warming. And now I will give you an analogy that I hope you will remember, because this is really, really important. Imagine two bathtubs, okay? The one is the analogy for CO2 and how it warms the planet. The other one is the analogy for methane. I start with CO2. Imagine a bathtub where you have a faucet, but no drain. A faucet, but no drain. Every time you turn on the faucet, whether on low or high, you add water to the bathtub and the levels rise. That's what happens to CO2. Every time we burn fossil fuel, we add new additional CO2 to the atmosphere, which increases the levels in the atmosphere and the resulting warming. Now comes the methane bathtub analogy. Here you have a faucet, but you also have a drain, and that drain is the atmospheric removal. When you turn on the faucet, the amount of water going in and the water extracted out through the drain are in balance, and that means the water levels stay stable. If you crank up the faucet all the way, then water levels can rise, because even though the drain is still open, you put more water in it than can come out. And that's what happens in part of the developing world, when increasing demand for animal source food is met by an increasing herd size. There the levels rise. But in the developed world, such as here in the United States, we either have constant herds, or we have constant herds or even decreasing herds with mitigation on top of that, reducing methane. And that means you are now turning on the water, but only slightly, and the drain is open all the way. And that means that your levels can go down. Your levels can go down. In the atmospheric community, that's called negative warming, when the warming goes down. And I will show you what that looks like in a minute. Three scenarios are depicted on this slide. An increasing amount of methane on top, then a stable amount of methane, or maybe slight reductions in the center, and then a strong reduction of methane, let's say 35%, and all three scenarios over 30 years time frame, okay? So I now first show you what these three scenarios look like under the GWP 100 scenario or unit that's being used since the 1990s. All three units are depicted as if an increase, stable, and a decreasing amount of methane were to lead at strong positive amounts of CO2 equivalent greenhouse gas emissions. Okay, and that shows very clearly that GWP 100 does not take into consideration the atmospheric removal, meaning GWP 100 acts as if there were no drain, even though there is a drain. GWP Star takes care of that. And here's what GWP Star predicts. When you increase methane strongly, that's like cranking the faucet on all the way, and you increase the amount of warming as a result. And that's that blue area north of the x-axis. You can see GWP Star and GWP 100 agree with one another when emissions increase. And that's what they did for a long time. But in the developed world, they no longer do that. Here we have either stable or slightly decreasing amounts of methane, and that, according to GWP Star, leads to negative warming, which is also indicated by the negative sign in front of the number. And as you can see here, there's quite a difference between GWP Star and GWP 100 when you have stable emissions. Okay, remember, stable emissions lead to stable concentrations of methane, and that leads to stable warming, no increasing warming. Okay, and that's what we see in the United States. In some parts of the United States, we see the bottom scenario where we have a decreasing amount of methane over time, and that actually now leads to strong negative warming. Strong negative warming is depicted here. The blue is now far south of the x-axis. And as you can see, a drastically different narrative between GWP 100 and GWP Star when you reduce methane. So the question now is, can we reduce methane by 20, 30, 35, 40%? And the answer is yes, we can. And I will show you that in a minute. But before I do that, I show you another slide that shows how CO2 and methane are different with respect to how they warm the planet. The first part of this slide here shows an increasing amount of CO2 and an increasing amount of methane from two different sources. Let's say a power plant that over 30 years increases its load and therefore the amount of CO2 produced. How does that increasing amount of CO2 warm the planet? It leads to an exponential increase in the warming from that CO2. Why exponential and not linear? Because it accumulates in the atmosphere, being a stock gas. An increasing amount of methane from a livestock herd, for example, as we see it in the developing world, leads to an increasing amount of warming, and we do not want to see it. It's a potent greenhouse gas. We do not want to add additional CH4 to the atmosphere. Under constant emission scenarios, let's say our power plant were to be on constant loads over 30 years, it would produce a constant amount of CO2 as a result. But that constant amount of CO2 would lead to an increasing amount of warming. Because it's a stock gas, it accumulates. But a constant livestock herd, like we've seen here in the United States, would not lead to increasing warming, but as you can see here, it would lead to constant warming. Again, constant emissions lead to constant concentrations in the atmosphere, and that leads to constant warming of our planet. What happens when we reduce both CO2 and methane? That's what gets me most excited. If we reduce CO2, for example, our power plant is ramped down over 30 years. When you reduce CO2, then the warming still increases over time, all the way up until the point that we shut that power plant down. That's what it takes for that CO2 to no longer lead to increasing amount of warming. So if we want to stop increasing amounts of warming, then we need to go net zero on CO2, But do we have to do the same thing for methane? The answer is no. Any kind of decreases of methane over time lead to negative warming, and that is a fancy word for cooling. So if we achieve a reduction of methane from our livestock herds, then that can be a real solution to our climate problem. People ask me, Frank, is methane a super pollutant? And I give the answer, in my opinion, CO2 is a super pollutant because even if you decrease CO2, the related warming still increases all the way until you go to net zero. Then it plateaus. To me, methane is a super opportunity because any kind of reduction will lead to a reversal of warming. And that is really exciting, I think, to most. So the question now is, can we get there? Is that possible? Well, here in California, we have a new law called SB 1383. It mandates a 40% reduction of methane to be achieved by the year 2030. Our farmers first went wild when they heard about that, but they no longer do, because our state decided to incentivize the reduction of methane financially through capital investment in technologies like covered lagoons on the one hand, but also other means. And as a result, our dairy industry, for example, partnered with the state and received funding, but also matched that funding. And for example, many dairies went in and covered their lagoons. So what normally is an open lagoon that's off-gassing into the air is now covered. And what you see here bulging out is biogas. This biogas, which is approximately 60% methane, is now no longer going into the air, it's now trapped. And it's converted then later into fuel, so-called renewable natural gas. And that renewable natural gas is then used as fuel to fuel vehicle fleets, such as semi-trucks. This, ladies and gentlemen, is considered the most carbon negative fuel type there is. The conversion of biogas from dairies into vehicle fuels is the most carbon negative fuel type there is. And that means you are now pulling carbon out of the atmosphere, much like you would if you were to plant forests that take CO2 out of the air and hence lead to a cooling effect as well. So this is very strongly financially incentivized through the payment of low carbon fuel standard credits. It's a mouthful, low carbon fuel standard credits. I think they run at $200 a ton of CO2e right now. And as a result, our dairy industry is jumping onto this. And we have already received or achieved a 2.2 million metric ton greenhouse gas reduction annually. That means while we have a 40% reduction goal to be achieved by 2030, we are already halfway there. We have reduced dairy methane by 25% in the state of California. And this is not some estimate or so, this is metered data because the biogas is metered and the conversion into RNG is metered and this RNG is sold off. So this is verified by the state of California. Our dairy industry has done a remarkable job of achieving that and is continuing along the way, and in my opinion, will easily achieve the 40% reduction by 2030. And this is not just something that we'll achieve through manure processes, but also through enteric reductions. Enteric meaning the belching. Here at UC Davis, we have looked into many different feed additives that can reduce methane. Of the 100 that exist, 5 additives actually do work and reduce methane, some of them in a sizable way, anywhere between 10 to 50%. They're not available on the shelf at this point, but they will be in a couple of years. Right now, they are still in experimental stages. So I'm kind of bullish about this whole thing, as you can tell. I'm very optimistic, and I tell people, listen, methane is a real opportunity, and you should take that real opportunity. I'll give you a few trends, some for beef, some for dairy, just to wrap up here. On the beef side, we used to have 140 million beef cattle in the United States. Today, we have much fewer, only 90 million left. So much fewer cattle, but we produce the same amount of beef. That has a drastic impact on our, for example, footprint. What you see here is the data again, but this time over time in years. You see the slaughter numbers have gone down drastically here in orange, but the production has gone up also drastically in the other way. So we are producing much more with much fewer animals. On the dairy side, we used to have 25 million dairy cows. Today we have 9 million. We have fewer dairy cows today in the United States than we have horses. We have 9.5 million horses. So we went from 25 million dairy cows to 9 million dairy cows, but we are producing 60% more milk with those, meaning the carbon footprint of a glass of milk has shrunk by 2/3. This is an achievement that we could share with the rest of the world. Countries like India, for example, they don't have 9 million dairy cows. They have 300 million cows and buffalo producing milk at dismal rates, okay? About 10 to 20 times less milk per animal than here in the United States. And they really need help because they are currently extremely inefficient, and that gives the global livestock sector a real black eye. It's not just India, it's also many countries in Africa and so on that really need to work on efficiencies because their herd sizes are massive and the productivity is really marginal. The pork side, we have tripled pork production since 1965. We have so much positive stuff to tell, good stories to tell as to how we produce food and so on. But many of our, I often call them special friends, people who don't like livestock, who don't like animal source foods, say we just need to stop produce animal source foods because they say this is driving climate change. And then I get questions day in, day out from reporters asking me whether or not we can eat our way out of climate change. Thankfully, several publications have addressed this issue. The first one I want to share is the one by Wines and Nicholas that looked into what would it take or what would the savings be if an omnivore were to go vegan, so totally plant-based for 1 year? Well, that savings would be 0.8 tons of CO2 equivalent units, 0.8 tons. Is that a lot or not? Let's contrast that to, for example, flying. One transatlantic flight per passenger emits 1.6 tons of CO2 equivalent emissions. And that means you have to go vegan for 2 years, to offset one flight that you might make to Europe. If the entire United States were to go meatless Monday, for example, that would save us 0.3% of greenhouse gases. And if the entire country were to go vegan, 2.6%. Am I having a problem with veganism? No, I don't. I think people should eat what they want to eat, okay? This is a part of your personal decision-making, just like it is who you vote for, who you love. Eating is a personal decision, okay? But the reason why I bring this up is because there are people out there saying, this is the move we have to make in order to save the planet. And this is absolutely the generation of a smokescreen, not less and not more. If you want to have an impact, a positive impact on our environmental footprint, on our climate footprint, then you need to further do what we have been doing and what we are world champions in. And this is improve efficiencies, work on feeding, on animal welfare and health, work on genetics. These are the moves that really matter. If you're interested in how to minimize the footprint of our food supply system, then take a look at this photo. This is depicting the average US family in front of all the food waste generated by that family. 40% of all food we produce in this country, 40% of all the food we produce in the entire developed world, and 40% of all food produced in the developing world goes to waste. In the developed world, mainly because of consumer waste, so that's in kitchens and restaurants. And in the developing world, it's more at the production level. So on the farms, people can't get crops harvested on time or processed or transported to the markets and so forth. I think that we can all agree, whether we are carnivores or vegans or anything in between, that a 40% food waste is unacceptable. That is by far the most important environmental issue around our food supply and food system. So with that, just really quickly, I'm on, of course, we have a webpage, the CLEAR Center at UC Davis, and we're writing a blog. You might find that interesting. And our center, of course, has a webpage, clear.ucdavis.edu. Please come and visit us there or on Twitter, or please ask me questions once we have the time to chat today. So thank you very much, and I'm looking forward to our discussions.